Greetings everyone, my name is Lazaros Moysis and our topic today is false strange attractors as sources of pseudo-randomness. So, first of all, we are going to discuss about strange and false attractors and define what is a false attractor. We are going to generalize and formalize the procedure of generating false attractors from a chaotic system, discuss a specific application in encryption that we're really interested in, and then we'll end our talk with a discussion of our future goals. So, first of all, false attractors. What are they? Okay, so this is a very recent work by these authors right here. It's called Discovering the Beauty of False Strange Attractors. It is very recent, just a few months ago. And in their work, the authors considered a specific novel technique of rearranging the trajectory of a chaotic system. So what they did is they provided a method of sort of shifting the values of each state independently from a chaotic solution. So they didn't perform complete shuffling or permutation, but rather they performed some shifting of the chaotic time series. And their goal was to create new shapes. And they termed these shapes false attractors. Why are they called false? Well, obviously because they are not real solutions of a chaotic system, but rather they span from an actual solution of the chaotic system, and then they perform some shuffling or shifting of the solution, and then they obtain a new shape. Now, in this work, the authors were actually interested in the interplay between mathematics and arts. So their main interest was to design new, novel, and very interesting shapes, the false attractors that span from original chaotic systems. But, this application is actually very interesting and we believe it has a lot more potential. So personally, what we're interested in at the moment is the potential application of false strange attractors in encryption. And that's what we're going to discuss in this presentation. So first of all, let's formalize the technique. The authors have a very clear discussion of how they create false attractors. In our paper, which is under construction at the moment, we formalize this and make it a bit more analytically presented so that it can be easily replicated by other authors. So starting from a dynamical system, okay, let us choose an integration step, a simulation time, a solving technique like ODE 45 in MATLAB. We solve the system, we obtain a solution as a time series, right? So after I obtain this solution for n seconds, let's arrange everything in a matrix. So this is actually the complete solution of the system for the simulation time, for the specific integration step, and for all the states. So if I plot this solution in 3D space, so any combination of the any three states, I obtain the chaotic attractor of the system. So how do we go from having a chaotic attractor to a false attractor? Well, simply what we do is, for each individual state, we perform this sort of circular shift. Slightly different from what the authors originally did, but we are doing it through a circular shift just so that we don't affect the final length of the trajectory. So we perform a different circular shift in each state, and we also consider any different combination of states. So that's why I have here Z1, Z2, Zn. So zeta here, Z can be any combination of states. We can consider the original states or have some duplicate of a single state. And for each individual state, we perform a left circular shift. So these are the key actual parameters of the technique. What are the states that I'm going to use? And what amount of circular shifting I'm doing in each individual state. So in this way, I get a new time series that I can actually plot and obtain a new shape. This new shape is called the strange false attractor. So it is called false because it doesn't actually correspond to a real solution of a system, but rather it spans from a real solution after I apply some sort of digital shifting of the states. Okay, and this is why it's called false, because it is not a real solution. So that's the technique that the authors proposed. Additionally, because our aim is to actually increase the key space of the technique, we perform one additional universal circular shift. So after I obtain this matrix zeta, I actually use it one additional step to perform a universal shift to the left by m positions. And this actually does not really affect the shape of the attractor, But what it does is it changes its initial position. So this can actually increase the key space that we're going to discuss about later. So let's give you some examples. Okay, this is the classical Lorenz attractor. Everybody knows this. What if I perform this sort of technique to obtain a false attractor? Okay. So this is an example of a false attractor. I actually perform circular shifting on 2 of the 3 different states. So this is a new attractor. This is not a real solution, but it is spun from the original solution after I perform circular shift. This is another example. So again, we get a very different shape compared to the original chaotic attractor. Here I perform a circular shift on the first state, and the others are left the same. So, the amount of different false attractors that I'm going to get is actually, almost very, very, very big. So let me give you some example of how the attractor changes. So here I shift the first state little by some seconds, and you see that the more I circularly shift one state, the attractor becomes completely different as the time moves on. Okay, so all of these shapes that you see here, these are all possible different false attractors, and they all span from just a single solution of the chaotic system, the Lorenz system, after I apply circular shifting on a single trajectory, the state x1. Let me give you another example. Here is again the Lorenz attractor. I shift the second state, and you see that we have all of these different possible solutions as false attractors. Okay, so many different shapes to choose from. And of course, if I consider different combinations of shifts, I obtain more and more different attractors. This is another example. This is a different original chaotic attractor from the Lorenz system for different parameters. And again, let me give you some examples. Another false attractor. You see it is very different from the original one. I perform shifting on 2 of the 3 states. And another attractor. Again, it spans from the original one after I perform some circular shifting on the second state. So, bottom line, just from a single solution of the chaotic system, by performing this circular shifting, I can obtain numerous different false attractors. And we already tried this in the Lorenz system. The authors originally tried a couple of different systems. We as well, I'm only reporting the Lorenz system, but we have actually have considered and already have a very large gallery of false strange attractors from different chaotic systems. So numerous possibilities here. So why the heck is this interesting for encryption? Okay, so why is it? Let me explain this. The whole idea is how we can improve the key space in an encryption design. So in chaotic encryption, we use the secret key, which corresponds actually to the set of all parameter values for a chaotic system that are required to perform encryption and decryption. So this is called the secret key. For example, I use specific initial conditions, specific parameter values for a chaotic system, I perform my encryption, and then at the receiver end, they need to replicate this chaotic system, so they need to have knowledge on this secret key, the parameter values and the initial conditions. So based on the secret key, we have to define the key space. So the key space is actually the set of all the different possible combinations of these parameters and initial conditions that can generate acceptable chaotic trajectories. So this is a very big number. We need to have it a very big number in order to be able to resist brute force attacks. But the very big issue here in chaos-based encryption is that the key space is actually very hard to specify. Okay, so it is very hard to specify what are all the possible combinations that give chaotic behavior. Some of them will not give chaotic behavior. Some of them diverge to infinity. Some of them have periodic behavior and are not acceptable. So the actual correct key space is very hard to specify. And this is a problem here in the literature because many publications report the key space very wrongly. Because they report it incorrectly, because they include the situations and the parameter pairs that give periodic behaviors. These are unacceptable in encryption. So we're trying to find a solution to this problem. Okay, so if we're going to use a chaotic system to perform encryption, how can we have a well-defined key space that all values are acceptable? So we believe that the solution here is to use false attractors. Okay. So one solution is this. We identify a parameter pair and initial conditions that give chaotic behavior, Okay, so we generate a chaotic trajectory, but these parameter pairs and initial conditions are not part of the key. What is part of the key is the parameters that we are using to generate the false attractor. So these sort of circular shifting parameters and the universal shifting parameters, these are the key parameters of the secret key. And since the system is already chaotic, performing any sort of rearranging, we also give a chaotic trajectory. Okay, so we believe that by doing this, we can not compromise the chaotic behavior of the system, while at the same time have a very large key space to resist brute force attacks. And we are only doing this from a single chaotic trajectory. Okay, so we believe this approach can bring a very, very big contribution to a very major problem in chaos-based encryption, that of accurate key space definition. So, for example, our proposed key space is this: the amount of states that we are using, x1, x2, x3, whatever, the amount of circular shifting we perform in each individual state, m1, m2, mn, and also the universal shift m that we perform. Okay, so this actually set of key parameters is very, very, very big. Okay? So it gives us a lot of different possibilities. For example, if I am to simulate a three-dimensional system, like the Lorenz attractor, for 999 seconds, and I choose a step size of dt equals 0.01 seconds, the amount of all possible false attractors that I'm going to have is 81 times 10 to the 8. Very big. Okay. So even if someone wants to do a brute force on this, it requires really, really a very long amount of time to identify what is my correct attractor. Okay, this is the theoretical number right here. So that's our solution to the problem of accurate key space definition. We believe that this can bring a major improvement in chaos-based applications by helping every author identify a correct amount of key space, which is actually very, very large. Okay, so this is our main contribution here, along with this sort of formalization of the procedure of generating chaotic attractors. Okay, now some comments. Someone may say, okay, why is this different from a classic permutation? Okay, in permutation, let me remind everybody, you perform actually a shuffling on every state of the time series, right? And every value of the time series. So permutation is actually a very good technique. It is very commonly used in encryption, but permutation has some issues, okay? Since in classic permutation, we apply shuffling to all of the elements of the time series, this is highly, highly more time consuming. Of course, it is more effective. It's like taking a deck of cards and having a complete shuffling of a deck of cards, okay? So it is very secure, but it is extremely time consuming, okay? So this sort of circular shifting we apply here to create false attractors, we can consider this a lighter alternative to full-on permutation, okay? So it is less effective, I mean, less secure, but it is extremely more quick to perform, extremely less time consuming, and extremely more computationally efficient. So we can consider this a lighter alternative to permutation, which is a very big gain as well. Now, to test our false attractors, we did one more application, very common to encryption, a pseudo-random bit generator. This is our, as we can say, a cornerstone in chaos-based encryption using random bit generators. So we designed here one just to test our false attractors. And I have here a bit generator that generates 48 bits per iteration, sorry, 42 bits per iteration. And I have it designed in such a way that it uses all three states all times in order to generate the bits. So we have a bit generator here that has this sort of avalanche property. If I change a single part of the bit, like perform a different circular shift, for example, the bit generator is going to change completely, so it has this strong avalanche property. And to see if it is a good enough prbg, I tested it on the Lorenz system and three different false attractors. So K1, K2, and K3 are the keys for the different false attractors that I considered. I tested the prbg through the NIST test of the NIST statistical tests. It is a very common set of 15 statistical tests that is performed on bit generators. All of them pass the generator successfully. So this is a very strong indication here that if I originally have a chaotic system and I have a bit generator that generates bits securely, then this generator is safe to use with any other false attractor that is spanned from the original chaotic trajectory. Okay, so this is a very good result. This means that I can only have to design a good prbg and one chaotic trajectory. Once I have one chaotic trajectory, I have a plethora of different false attractors that I can use as sources of randomness. And in all cases, I do not compromise chaoticity of the system. So we believe that this can be a very, very good solution to chaos-based encryption. Okay, so which are our future goals? First of all, let me discuss what we did in our paper. Okay, overall, we're actually writing the paper right now. We believe we're going to have a full text in just some months. So we actually based our approach to the original paper by creating false attractors. The paper is very good originally, but we try to have a more of formalized technique for constructing false attractors so that everybody that reads our paper can replicate it for themselves. So this is an initial very good contribution. We generalized the approach provided by the authors by adding one more universal shift. So this is just adds one more level of security in the overall design. So overall, we managed to increase the original key space of the approach. So it is now much, much wider. And of course, it provides a very big key space without compromising computational efficiency. And additionally, we applied our false attractors to the design of a prbg. Everything works successfully. So once you have a chaotic trajectory, you can have many, many different false attractors, all of them suitable for the design of a prbg. Okay. So these are all our main contributions. Okay. Our future goal is something that is very, very novel and very experimental. But over the last few years, there have been some techniques called SINDI, sparse identification of nonlinear dynamics, that are used in order to generate and identify chaotic systems, just from a time series. So what we're trying to test right now is whether we can see if, given a simple and a single false attractor, if it is possible to generate an actual system that has this solution as a false attractor. Okay. So if we manage to achieve this is going to be something very important because we are going to have, a design that starts from a false trajectory, so a trajectory that is not actually a solution of the chaotic system. And using this trajectory, we may be able to generate a new chaotic system that actually has this false attractor as its actual solution. So this is going to be a very major contribution in the case of nonlinear dynamics. This is at the very starting point right now. We're actually on the test stage. In some cases it works, in some cases it doesn't. Hopefully within a few months we are going to have some more interesting results to report. But again, this is going to be what I believe a major contribution in understanding nonlinear dynamics and in managing to create novel chaotic systems pretty much out of nothing, out of having false attractors. So thank you very much for your time, and I will be waiting for your questions.